So today we're joined by Fabian Ruehle, who's assistant professor in the physics and maths department of Northeastern University College of Science. He's a senior investigator at the Institute for Artificial Intelligence and Fundamental Interactions, and his research interests lie at the intersection of maths, theoretical physics, and machine learning, which I believe we're going to get a bit of a cross-section of today. So without further ado, Fabian, please feel free to get started.
All right. Well, thank you very much for the invitation, and thank you very much for having me here. As you said, I will be talking about the cross-section of math, physics, and AI, and I mostly base this talk on a perspective article we published in Nature Review Physics earlier this year. So when I submitted my abstract, I wanted to talk about a specific aspect out of this paper. There are many things in here, and I wanted to talk about essentially how to get rigorous results by leveraging reinforcement learning. But now recently we had this paper on cans, which created quite some interest in the community. And I wanted to say also a few words about cans, which fits into a different aspect that's described in this paper. Good, so let's get started. So in a sense, people in my field, theoretical mathematical physicists or even pure mathematicians, are very late adopters of things that we are witnessing in the AI revolution. Essentially, my field started using AI or machine learning in around 2017. And the reasons for these, why we didn't do this earlier, or why this is even still now in its infancy, is, as far as I'm concerned, and as far as my colleagues are concerned who I talk to, mostly due to the fact that in mathematics or in high energy theory, we need provably correct results, and the results need to be interpretable. Moreover, we need the data set that we have, sort of this mathematical data that describes properties that are inherently true for some mathematical object, is very different from real world data. On the other hand, if you look at modern ML techniques, and by this I just mean large neural networks, they typically are black box, meaning you cannot really interpret, you have no idea what's going on. So this is against this interpretability paradigm. They are stochastic, and also they are prone to errors. And this together gives you a problem in sort of getting provably correct results. Case in point, I generated this image with a Copilot. And you can see it looks amazing, but of course, sort of it's just lying to you. Or it's cheating. It gave itself like an extra row of pawns here. And the task was to generate an image of a scientist and an AI playing chess. So while the result looks good, there can be errors in there that you might not even see when you first look. And it's completely sure that it generated this image correctly, but there might be artifacts in here which sort of we cannot allow for. There's zero room for error in what we are doing. Concerning the second point, real-world data is also different in the sense that if it comes from a detector or from an image or something, there's typically just noise, and noise from the camera, noise from the measuring apparatus, whatever, which is not the case for mathematical data. Mathematical data is computed data, it's completely exact. There's no stochasticity, there's no room for error. Outliers in your data set, you might just be tempted to remove them because probably sort of, I don't know, some muon hit your camera and eliminated a pixel, so you didn't want to get rid of it. In math, this cannot happen. Sort of, the outliers are all meaningful. So typically, if you have some pipeline that works in the real world, it's not guaranteed to work in for this mathematical data set. Moreover, you lack a precise definition of what it even means to have some certain features. So let's say you're asking, I have a cat image, and I want to see the set of all cat images. So what is the pixel space that will give you a cat image? And this thing is not well defined. You can just flip a bit, or you can choose an RGB value to go from 254 to 253, and it will probably still look like a cat. So this is like a fuzzy boundary, whereas sort of for mathematical properties, you can know exactly so if this object has the specific property or it doesn't. It's not like this sliding scale. In classical data sets, if you do supervised machine learning, you have humans that annotate images, let's say, and they make mistakes. So the labels can be wrong. Again, in math, this cannot happen. If you look at biological systems, typically, so if you have linear or monotonic responses, if you produce some, if your body produces some, let's say some protein or so, this causes a linear response or a monotonic response in something else. In mathematics, you don't have any control over what the functional dependence on your features are. So these are just a few reasons why I believe that sort of high energy theory and mathematics has not adapted this to the full potential yet. So the point of the talk is, what do we do about this? And well, we propose two avenues to follow. The first one is to use the ML algorithms to obtain some interpretable result. And as I said, by themselves, they're black box, so we need to do something about this. And one thing that has been proposed recently is these kind of architectures which allow you to get something more interpretable. And then you can essentially, once you can interpret what the machine or what the algorithm is doing, you might have a chance of turning this into a mathematical theorem. If you understand what it is doing, you can conjecture that this will solve your problem, and then a human or some domain expert can actually hopefully turn this into a theorem and prove it. Another avenue is to use reinforcement learning to obtain provably correct results. So essentially, here the idea is you use a neural network to give you a result that you want, and you're not trying really to understand how the neural network worked internally to get to this result. You just sort of, in the worst case scenario, you just care about the fact that it got the result and you can prove that it is correct. Or you can try to sort of understand what it was doing, not how it arrived at the technique that it used, but just sort of what it did. And I will illustrate these points by picking examples from knot theory. So the outline of my talk is, I will very briefly give an introduction to knot theory. Of course, this will not be a mathematical introduction. This will just sort of give you a few facts to understand the examples that I want to be using throughout the talk. And then I want to talk about cans and reinforcement learning as ways of getting rigorous or provably correct results. And then I want to conclude. Good. So let me start with knot theory. The reason why I picked knot theory over, let's say, my area of physics, which I work on, which is string theory, then I would have to explain 10 dimensions and Calabi-Yau manifolds and all these things. Knot theory is easier to visualize. Most of us have an intuitive idea of what a knot is. But there are also other motivations. They actually appear quite frequently in science. So first of all, they appear in theoretical physics. So this was a first result by Witten, who noticed that they appear in a three-dimensional theory. They appear together with so-called gauge theories. But they also appear, for example, in biology. When you have protein folding, you can fold a protein such that it ties a knot. A variant of this appears in quantum computer, where you have braided anyons. And they are also a very interesting object in pure math. In particular, there is something that is called the smooth Poincare conjecture. And Poincare asked the question whether everything that looks like a sphere can be smoothly deformed into a sphere. And there's a collection of Poincare conjectures, and this one is the last open one. And it's also related to knot theory, as we will see later. Good. So what is a knot? So a knot is just an embedding of a circle into some three-dimensional space. So what I mean by this, a knot is just exactly what you think it would be. You just take a string, you do something with it, but then in contrast to maybe the knots in your shoelace, what you do is you always glue together the endpoints. So a knot for mathematicians is always closed, but other than that, it is exactly what you would think. So now, given a knot, or given its projection to two dimensions, an interesting problem that's important for many of these applications here is, let's say you're given this knot and I ask you, can this be untangled? Can you sort of turn this just into a circle? And typically I ask people to raise hands whether or not they believe it can be untangled. In this particular case, the answer is yes. So if you look at this, you see sort of I can just take this thing and do operations with it to turn it into a circle. So this is one type of questions that we actually want to address with with machine learning. And I will explain how we do this using reinforcement learning later in the talk. Good. So what this example shows is that in the end, we are not really interested. When we are given a knot, we are not really interested in small deformations or even sort of twisting it or so. So we're interested, for our purposes, this knot is the same as if I sort of put a small dent in it, or even if I sort of twist it around like this. So I want to consider all of these the same knot. So all of these individual pieces that you encounter here, they are all essentially just the circle knot that I made more complicated. So mathematicians essentially want to have a way of classifying knots up to me making them, crumbling them up. So we want some so-called knot invariants that tell you essentially that these three knots are the same, but they're different, for example, from this knot. And mathematicians have come up with many, many invariants. And some of them are geometric in nature, and some of them are topological in nature. So, for example, you can show that if you take this knot inside the three-dimensional sphere, like so, you drill out a small surrounding of this knot, and now you calculate the volume of the unit sphere minus this knot. This is an invariant. There are other invariants that sort of have more of this geometric meaning. For example, you can look at lengths of curves on the knot. There are also topological invariants. They can be scalar invariants. You can assign something like a signature to a knot. There can be polynomial invariants, which are polynomials that you can construct that are not changed if you do something like this, or even something like this to a knot. There are homologies, so this would be vector quantities that are invariant under these things and so on. So we just have this collection of geometric data on the one hand to describe a knot, and we have this collection of topological invariants that also describe a knot. And a natural question is, are these two related? And if so, how are they related? So these are the two types of questions I want to illustrate. First of all, this unknotting problem, and we will essentially address this with RL. And this question about sort of relating different invariants in a mathematical data set, which I will do with cans. So this is all I wanted to say about knot theory. Knot is a sort of complicated object that is then glued together. We want to classify all of these objects up to smooth deformations like this. And we can do this with some invariants that we can define for this knot. And now we want to study relations among them. And one way of doing this is using what we recently proposed to be Kolmogorov-Arnold networks. So this paper is fairly new, so I will give a short introduction to cans, and then I will explain how to apply them to this problem in knot theory. Okay, so if you just look at the computational graph of a can, this looks very, very similar to the computational graph of a neural network. But in a sense, it's the opposite, or it's the inverse. So of course, if you have a neural network, you have these nodes, and then you have linear transformations or an affine map multiplied by matrix W on the edges, and then you apply some nonlinear activation function at the nodes. When you have a can, essentially what you do is you do the opposite. You perform a nonlinear transformation along the edges of the computational graph, and at the nodes, you have a linear transformation. You just sum them all up. So all the incoming things here are just summed, but we apply nonlinear functions that go into this node. And these nonlinear activation functions, they are learned. So we use some interpolation method for this. Rather than fixing the activation function to be a tanh or a ReLU or whatever, we learn these using some interpolation method, some so-called B-splines or cubic splines in the simplest case. So in the case of neural networks, you have the universal approximation theorem. This tells you that this neural network, even though this looks kind of unintuitive, or it's, as I said, very hard to interpret for a human being, which is kind of ironic because they were modeled after the human brain, but the human brain this is not how we think about functions, because it's sort of this nested structure of matrix multiplication, of tanh of matrix multiplication, of tanh of matrix multiplication, and so on. This one is sort of, you can more easily look at and see actually what's going on. And just like neural networks can express any function using which is sort of proven in the universal approximation theorem, if you just make the neural network wide enough, Cans can also express any function, and that's what the Kolmogorov-Arnold theorem says, and this is where the name comes from. Essentially, what the theorem tells you is you take a bunch of piecewise defined functions and you sum them together, and you can represent any function. Okay, so let me very briefly talk about cubic splines. This is something that when I studied computer science or numerical analysis was something that was taught there. I wouldn't be surprised if people nowadays don't know this anymore because neural networks largely eliminated sort of the problem of doing polynomial fits. So the point is, if you have a degree n polynomial, you can fit n+1 points exactly because you have in the degree n polynomial, you have n+1 parameters. I can adjust them so that the polynomial goes to these n+1 point to these n points, so the n+1 points, and that's done. But then by the fundamental theorem of algebra, well, if it was complex at least, and we count multiplicities, it would also have n-1 maxima or minima. And practice might have less, but it still sort of has a lot of minima and maxima. So if I take essentially this data set here, which was sampled from a noisy line, and I try to fit a degree 10 polynomials with these points, I get something that matches all of these points exactly. But of course, there's these huge fluctuations around this. And given that this was sampled from a line, getting an answer of 10 to the 5 here is probably not what you were looking for. So instead of sort of fitting a high degree polynomial, what you can do is, well, first of all, you can just fit a neural network. This is what I did here. I took a neural network with 2 hidden layers, 1 million parameters, so essentially hidden layers 1,000 and 1,000, tons activation, and then I got something like this fit. And this has even much more parameters. So this has 1 million parameters, not just 11. So you might be worried that this is even more severely overfitting. But there is this double descent phenomenon, which tells you, yes, sort of if you make the neural network a little bit too big, you start to overfit. But then if you make it vastly too big, this acts as a regularizer, and the neural networks actually don't overfit, but give you something that looks rather smooth like this. So by just giving your neural networks way too many parameters, they won't sort of produce this line, they will produce something that looks like this. If you use cubic splines instead, what you're doing is you're fitting a piecewise cubic function to each of these 2 points, let's say. So a cubic function is ax cubed plus bx squared plus cx plus d. So this has 4 parameters. I want each of these splines to go through 2 points, let's say this and then this and that. So that eats up 2 parameters. And then I want the derivative to be continuous. That eats up 2 more parameters. So using these 4 parameters, essentially I can produce a smooth curve that looks like this. And that looks very similar to what the neural network actually learned. Good. So essentially, this is what we do with activation functions. We approximate them here on the edges with piecewise polynomial functions, and we have these parameters in these functions which are learnable, which we then update again, sort of just using some optimizer to find these such that the function on the edges gives you a computational graph that computes some function that you actually want to compute. So yeah, in practice, what we do is we use this spline function and we add to it a quote unquote bias, which we take to be the pseudo function. This looks like a ReLU, but is smooth at the origin. So it's constructed from exponential. And then we use something to induce sparsity. And in neural networks, the way you get sparsity typically is you use an L1 weight regularization. So you add a term which is essentially proportional to the sum of the absolute value of all the weights in the neural network. And this has been shown to induce sparsity. You can do something similar for cans, where you add a term that essentially punishes the size of the splines. So big splines proportional to the absolute value of these functions. And then once we have induced this L1 regularization, and we also add something that's called entropy regularization, we can prune the neural network, the CAN, by looking at how big are the splines or the function values that come in here and how big are the ones that go out. So this is this I and this O, I for incoming, O for outgoing. So I'm just taking essentially the max over all of the things that come, the max over all of the things that come in and the max over all the things that go out. And if this is small enough, I will essentially just delete this node. So I'm not pruning edges, I'm pruning nodes here. And if I do this, I obtain something that's quite interpretable. And we have this example here where I have this composite function of sin of x1 squared plus x2 squared plus sin of x3 squared plus x4 squared. Yeah, so I have 4 features, x1, x2, x3, x4. I have a single output, which is this exponential function. I initialize my can, and in the beginning, these are just some random splines on these edges, and now I start adjusting the parameters to get this function. So you see what is going on here. If this fades out, this means that the absolute value here is very small. And in the end, I end up, let me pause it. At the end, I end up with something that looks like this. So you can clearly see, so if it takes x1 and x2 and it applies a square function to it, takes x3 and x4 and applies a square function to it. And then remember, this is just adding stuff up. So it takes x1 squared plus x2 squared here, x3 squared plus x4 squared here. Then it applies this function. So this is the learned spline. This is like a sine. So it takes it, applies a sine here to x1 squared plus x2 squared. It applies another sine to x3 squared plus x4 squared. And this looks like an exponential. So it applies the exponential to the sum, and you get the result. So this is how you can use this essentially to perform symbolic regression. So we can, just from training this neural network, we can get out a symbolic formula. And once we have this, we can now conjecture that this is the correct relation between the input features xi and the output y in this case. And then you could try to prove this mathematically. Okay, so let's make an example of how we do this type of conjecture generation with cans. And before I sort of tell you how to do this for the particular case of these not invariants, let me just say again what I essentially just outlined, how we do this for mathematical data set in general. So let's say you're given some mathematical data and you want to find relations within this mathematical data. So what you would do as a classical data, I mean, first thing you would learn in data science course or in a statistics course is you would compute a correlation matrix and see whether some of these features are correlated. But as I said in the beginning, our correlations can be very nonlinear. They can be non-monotonic. They can sort of be not correlated between two values or two inputs, but many of them. So this might be actually hard to detect in just a standard correlation matrix. So in essence, we have the following problem. We want to find relations. Let's say we have a function. We have some we have some features xi1 to xin, and we apply some nonlinear function to it. And this is equal to some other labels, to some other features xj1 to xjm, also applied to some function. So there's some relation between some set of labels, some set of features, and some other set of features. And if I wanted to, I could bring this to the other side. I could write this f minus g equals 0. And then I call f minus g, I just call capital F. So essentially, what we're interested in is a non-trivial function, capital F, such that it can sort of build 0 or any other number out of it. So an idea that was done before we essentially had cans was you just take this function, we don't know what it is, but we just sort of apply a neural network. A neural network, as I said, can learn any function. So you just apply this function to some set of inputs. You try to reproduce one of the other or some collection of the other inputs as an output. And if this thing performs better than random or better than just a monkey randomly picking stuff, there has to be some relation in there because the neural network was able to sort of predict this output from its input. So there has to be a relation between the input and the output. And just by knowing that there is a relation, you can then try to conjecture what this type of relation is and then try to prove it. So let me come back to this question. So let's apply this to the problem of relating not invariants. This is something that DeepMind actually did in their very nice Nature paper from 2021. So they asked about relations between geometric and topological invariance. And what they did is they picked one of the topological invariants, the signature, and they tried to see what the function f of these geometric invariants has to be in order to predict the signature. Once they sort of see that there is a map, the neural network manages to predict the signature from these geometric invariants. They have a conjecture. They can say, okay, so these geometric invariants somehow are related to the signature. Then they perform some feature attribution score or some feature scoring technique, which means you try to see which feature is the most important in calculating the signature. For example, you can do this by, or what they did is they just took a derivative of the neural network, and the derivative, sort of the gradient of the neural network, tells you if you change the input a little bit and the output changes a lot, this means that the dependence of the output on this particular input is big. And if you can change sort of this particular input feature without changing the output, this means that this feature is not relevant for getting the output. So this is how they arrived at a conjecture of the geometric invariants that go into predicting this topological invariant. So in general, if you wanted to do this in complete generality, what you would have to do is you would have to take all your input features, and then you would have to calculate the power set of these input features. So the power set is all possible combinations of input features. So this would be the empty set, like just each feature individually, the combination of 2 features, the combination of 3 features, and so on. And there are 2 to the n of these. And then you try to learn sort of a map from any of these sets to any of the other set, to any other set. So let's say you want to map x1 and x2 to xn, which would be an example for picking the signature as an output and sort of finding the inputs that map onto this. But in general, sort of you have then to train 2 to the n times 2 to the n neural networks, a little bit less, because I mean some of these are trivial, but so if you get an exponentially many things to look at. So DeepMind didn't do this, they just sort of picked the signature, so they just essentially were looking at all of these, doing some feature attribution, and then always using the single output. But the most essentially brute force, or the most principled way of doing it, would be solving a problem like this. That's not what we did. So for Kans, what we did is we essentially took this approach where we tried to learn a function f that is equal to 0, or that we set equal to 0. And then if we can find a non-trivial function f that does this, we know there's a relation between these inputs or these features. The problem is, of course, we initialized this very close to 0. So we're very close to f being the 0 function. So it tends to learn a trivial function. I mean, just setting everything to 0 works, of course, but this is a trivial relation. This is not a relation we are interested in. So what we do is we take this problem, we turn it into a binary classification problem. So instead of essentially finding this function f directly, we find a function g, which is 1 if x belongs to a knot. So if we have all these features, that topological and geometric invariants that have been calculated for a specific knot, and then we want to find a function g that produces 1 for this set of features. And if we give it some random data that doesn't, sort of a collection of data that together do not describe a knot, that have just been sort of randomly generated, we want it to give out 0. So if we give it this collection of features that belongs to a knot, the binary classification gives 1, 0 if it doesn't. So how do we generate this fake data? Well, the way we do it is we do feature corruption by feature permutation. So what this means is we have this collection, let's say we have this for one knot, we have calculated the features x1 to xn, then we have calculated for the second knot the features x1 to xn, and so on. So this is our actual training set. And now we add false knots, if you wish, where we just randomly permute all of the first features across all of the different knots. So let's say instead of taking the first feature, you take the 17th, then instead of this, I take the first feature from the 17th knot, the second feature from the 5th knot, and the nth feature from the 108th knot, and so on. So now this collection here does not describe a knot anymore. Neither does this or any of the other ones. But the advantage of doing this is, of course, the overall collection of features hasn't changed here. Because otherwise you might be worried that your neural network is actually picking up on your generation algorithm rather than essentially learning something fundamental about the classification problem. So if you just randomly generate this, the neural network might see that these numbers are not randomly generated. These ones are with respect to some underlying probability distribution, and might just sort of learn to tell apart these two probability distributions without actually learning something about the problem. So this is why we did this feature permutation. Good. So now we have this problem where we essentially learn g of x, which is 1 or 0. But the original problem was to learn this f of x, where x is equal to 0 if it belongs to a lot, and not equal to 0 if x doesn't belong to a lot. So there are different things we could do. So what we did is we applied as a last quote-unquote layer in the CAN, or as a last computational step in the CAN. We fixed the function to not be a spline that is learnable, but we fixed it to be just this Gaussian function e to the minus x squared over 2 omega squared. So what this does is, if omega is very small, this is a highly peaked thing around 0. So then you see if f is approximately 0, then g of x is just sort of the sigma applied to f of x is roughly 1. So because you're inside of this peak, which is peaked at 1, this Gaussian peaked at 1, and centered around 0. So f being 0 is equivalent to g of x being 1. And if f is very far outside in this peak Gaussian, then essentially g of x will be 0. So we can read off this function f of x that we wanted to know by just looking at the first n-1 layers in the CAN. And the last layer, we just choose to be this peak delta function. So this is how this looks in practice. Let me see. I'm on Zoom, but I don't think I can zoom in. Okay, so we gave it this set of mathematical data here of the knot, and we asked it to find this function f such that it is 0 in a binary classification problem. We just randomly initialized the CAN multiple times, and for each initialization, for each seed, it gave us a different answer, and essentially it found, we did this 200 times or so, and it found these three relations in the data set. So this relation here is equal to what DeepMind found. So you see sort of after this pruning and regularization techniques, it tells you which quantities enter into the output. And you can look at the activation function to make a conjecture of what the functional dependence is. So let me illustrate this actually for this. This one is a trivial example. So what this is, there's something that is called a cusp volume and something that's called the translations. And they are just sort of, if you multiply the translations, you get the volume. So essentially, when you take this drilled out region, you take the circumference times the circle, and this is how you calculate the volume. So if you look at the CAN, what you see is that, well, I wish you could read this better. I thought I could zoom in, but somehow it's not letting me zoom in. So this one here is the longitudinal, and this one is the meridional translation. And then it's learned this spline, which looks like a logarithm. And this one is the volume, and it learned minus the logarithm. And then it adds them all up, and it applies this very peak delta function. And this is how it solved it. So this part here, this red edge, we fixed to be the delta function. And after pruning, we find that essentially there's a relation between the cusp volume and these two translations. And if you look at the splines, this looks like a logarithm. This looks like a logarithm. This looks like a negative logarithm. So this then lets us conjecture that minus the log of this volume plus the log of this translation plus the log of this translation is equal to 0. So now we bring the log to the other side. So we have the log of the volume is equal to the log of one translation plus the log of the other translation. And then you can use the logarithm law that tells us essentially that this is equal to the log of the product of the two. And then you can exponentiate both sides, and you find that the volume is equal to the product here. So this is a little bit complicated because these things can only add, they cannot multiply. So in order to find this multiplicative relation, what the CAN had to do is it had to learn sort of the sum of the log and then taking the exponential, which would essentially reduce it back to standard product. So they are interpretable, but given that you can only sum here, you might still have to sort of take a roundabout way of doing a mathematical operation that you have to do. But even if you couldn't have figured it out this way, it's very clear that sort of there's a relation just among these three things. So now you could try to use other symbolic regression techniques to find a formula for these three. Good. So this is all I wanted to say about cans. If you want to try them out, there's a GitHub page where you can go and download cans and you can play with them yourself. And this concludes the section. I actually wanted to talk about conjecture generation, and then subsequently proving it by a domain expert. So we need something interpretable, which we have in this case. We see which stuff has a relation, which stuff enters. And now we got this from the can. As I said, DeepMind got this from their gradient saliency analysis of a neural network, and they then proved a relation between a previously unknown relation between the geometric invariance and the topological invariant of the signature. So as I said, we also sort of see from the can that they are related. You find this relation, this is trivial because it's a definition. You find this relation, this is not non-trivial in the sense that it's not a definition, but it's a known theorem. So we didn't, in this data set of not invariants, we didn't find anything that has not been known before, but it's still interesting to see that we recovered all the known things. Okay, so let's move away from conjecture generation and move on to the second problem, which is essentially using reinforcement learning for some of the problems that we encounter in math and physics. So I come back to this unknot classification problems. The question was, can I unknot this and turn this into a circle? And on the face of it, this again sounds like a binary classification problem. So you give it the circle, you train a neural network to predict one, you maybe sort of do some of these smooth deformations that we sort of want to all think about as the same knot. So let's say I twist it. I play a neural network, I tell it to learn one, I give it this knot, and I'm telling you, no matter what you do to it, you cannot untangle it. So that's a 0. And then you train this neural network, and then you have a classifier that tells you whether or not a given knot is unknotable. But of course, in practice, this is not what happens. You give it this knot, and if the neural network learns this very well, it will sort of output 0.96. It will not output 1. So what does this tell you? So sorry, that's a type. So does this tell you sort of this is 96% of an unknot, or it's 96% sure it's an unknot? So for mathematicians, this answer is completely useless. Even if it had answered exactly 1, it would still be useless because we would have no way of knowing that the neural network is not just straight out lying to you. And as we saw, they are very good in hallucinating previously. So this is about as useful as sort of training a Go algorithm where you sort of show it this board and then you ask it, can white win from this position? And if the neural network says yes, that's cool, but you haven't learned anything. So you know exactly 0 about the problem. So of course, this is also not what DeepMind did when they beat the world champion Go. So what they did is they needed something to actually play the game. So if the neural network said, yes, you can win, we actually sort of, the reinforcement learning algorithm tells you how to win the game. And this is essentially what's underlying our idea as well. So in general, reinforcement learning is just a way of dealing with combinatorically large search spaces. If you look at this Go board, let's say it's white's turn. So now white can put a stone anywhere on this grid. And after that, black can put a stone anywhere else in the free space. So there's a huge, huge combinatorical problem of where you put the stones. And if white can win, this means there exists a sequence of moves that wins independent of what black is doing. So they are a 19 by 19 grid. So there are 371 grid points. So at each point, essentially, each move, you have 371 possibilities, and then you have 370. So this is essentially 371 factorial ways of doing this. Or put differently, there are 3 to the 371 possible Go boards in the possible Go board configurations. So now the number of atoms in the universe is 3 to the 80. So this is just a gigantic number, and there's no way you can actually find this by brute forcing the problem. There's no way that you can try to outcompute the human by sort of trying all possibilities of putting white stone, then all possibilities of putting a black stone after that, or putting all possibilities of putting white stone. This just goes beyond imagination, and there's no way of doing this. So instead, what Silva et al. They used reinforcement learning. So they had some sort of search tree where you have all the possibilities of placing the white stone next. And then they asked the neural network, okay, essentially, where should I put the stone? And the neural network recommends, well, you put it here. So you pick this. And then you turn the ball around. You have or you have this neural network play against another neural network. You ask, where should I put the stone? It says, well, you put a black stone here. So you do this, then you ask, where do I put the white stone? The neural network says you put it here, and so on. So you take the recommendations of the neural network to traverse this huge search tree. That's the idea of reinforcement learning. And what this does is, in mathematics context, is you have a so-called policy neural network that solves a Markov decision problem. Policy just being, it tells you which move to perform next. So taking a step back, the way we set this up now for any problem with these combinatorial large search spaces is, as I said, we want to have a provable result. So we set up a reinforcement learning algorithm that solves the positive instances of a decision problem. So can I untangle this knot? Or in general, does this mathematical object O have some property X? The answer is yes. The algorithm should halt, and it should produce a truth certificate for this answer. So it should essentially tell us, yes, you can win the game, and here's how you win it. If the answer is no, we don't make any assumptions. So the algorithm can run forever. It can do whatever it likes. If I give it a knot that I cannot untangle, that's perfectly fine. But if it can untangle it, it has to sort of give us a sequence of moves that untangles it. So I have described this here for the unknot decision problem, but it works essentially for any problem in discrete mathematics and physics. It might even work for continuous problems. So there are continuous versions of reinforcement learning, but we have only tried it for the discrete problems, and there it works incredibly well. For continuous problems, typically you can try to do some minimization procedure or so on. And they appear in topology, in group theory, representation theory, number theory. They're everywhere in math, and they're also everywhere in physics, these discrete problems. Because as soon as you have a quantum theory of something, being quantized is precisely what you mean. You can have one quanta, two quanta, three quanta, but you cannot have 1.5 quanta. So you essentially have a discrete problem. And we encountered this in string theory, and we solve this problem as well using a very similar idea to how we untangle a knot. So overall, you can say that this method works very well if you have a so-called NP problem. NP means that you can, if somebody gives you a solution, you can very quickly check that it is a solution, but you don't have no way of generically finding the solution very, very fast. So if somebody gives you a solution, you can check, yes, it is a solution, but you have no way of finding the solution yourself, unless P is equal to NP, which is a famous open problem, but I don't know anybody who believes that P is equal to NP. So let's assume that's not the case. So you cannot sort of solve this problem quickly. The best thing you can do is you can just brute force all possibilities. Or if you take a neural network, you can learn heuristics, how to traverse the search tree, get to a solution. And then once it gives you the solution, you can check that it actually is a solution. Good. So here's how the RL algorithm works in general. So you have this discrete set of states and some landscape here. You start with some input state. You ask, what are the next possible actions? Where can you go next? Where can I put a stone? Then your network suggests something. You perform this action. And then the algorithm receives a punishment or a reward depending on whether it did good or badly with this move. So let's say you want to go down as far as possible in this case. So it went a little bit down, so it gets a reward. It learns that it got a reward, and sort of from this, it's learning the rules of the game. It's learning what actually its objective is. So it adjusts its behavior. So it learns, okay, going down is good. We take this as a new input state. We ask it to find the next action. It suggests this. We perform this action. So now it walked up, so we punish it. We tell it walking up is not good. It learns this, adjusts its behavior, and then it traverses this until it finds some terminal state where you end the game, where you, let's say you won the chess game or the Go game, or you entangled a knot or something. And now you set it up such that along this trajectory of actions, the algorithm is not optimizing necessarily just its next reward, but it's optimizing its accumulated rewards. So this is very, very important, get trapped in local minima. If it would never sort of do this thing, if it would never walk up a little bit to get the big diamond in the end, you could get trapped in this local minima and you would never sort of find a good trajectory here. But if you optimize the accumulated returns over all the different actions, indeed it will take a hit here if it can get a big reward in the end. And if you look at the way that, let's say, AlphaGo play or Chess plays chess games, they do play pawn sacrifices or other types of gambits all the time. So they take a hit in order to get a better position on the board and eventually win the game. That's also very important in the unknotting problem, because sometimes you might have to sort of make the knot more complicated in order to unknot it. This was not the case in the video that I showed you, but there are cases where you have to make it more complicated before you can simplify it. It's important that we sort of tell it, well, you should, in the end, you want to get to the unknot, but it's okay if you make it more complicated along the way. Good. So now we need to formulate this somehow as a reinforcement learning problem. And this looks very continuous. You just sort of smoothly untangle it. But in fact, even though it looks continuous, it's actually better to formulate this as a discrete problem, because we don't actually care about the shapes of the node. The only time something non-trivial happens is when we move, so when we reduce one of the crossings here. So when we move this strand in here, then something non-trivial happens. But whether I move this slightly up or down, the knot doesn't change at all. So actually, Reidemeister proved that just doing these three types of actions, you can convert any knot into any other equivalent knot. So either you can sort of, you have this loop here that you can pull straight, or you can put a loop into it. You can take a knot that's like this and you can slide it apart, or you can take like a crossing that's like this and you can sort of slide this up and down. So these, where you slide this bottom here up here. So these three moves are enough to get to any equivalent knot configuration. So if you look at the video, essentially what we did is we did this type of sliding move where you sort of put this past here. Then we did this type of sliding move here. That's called a poke, that's called a slide, and so on. And then in the end, we did this twist here, and we got to the unknot. So now if we ask the neural network, given this knot, is it the unknot? We wanted to say yes. And here's how you prove it. You do this, then you do this, and you do blah, 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 then you do this, and then you do this. And you see it is the unknot. And that satisfies any mathematician. It's completely provable. If you had the physical knot in front of you, you could actually perform these manipulations and convince yourself that this indeed unknots the knot. So the way we set now up this reinforcement learning problem is we define a reward to just be the number of crossings, so the number of over and under thingies here that you still have in the knot, because we want to get to 0. And we set up a neural network which takes some representation of the knot as an input, and it outputs out of all possible actions that it can perform, it outputs which one will work best. And then we just sort of traverse this tree by performing this action, asking which one do I do now, which one do I do now, over and over again. And the specific type of RL algorithm that we use also requires something that's called a value function. So we ask it, sort of given this position, how likely is it that you can win? And this is a very complicated question that in general we don't have an answer for. So we also use a neural network to approximate this function. And the terminal states that we won the game once we reach the unknot, or as I said, if the given object cannot be unknotted, it would just run forever. So we also terminate it after some given number of steps. So in this case, we terminate it after 300 actions. And so here's what we found. If you just try to do this randomly, as the number of crossings goes up, you see that sort of this gets exponentially, the success rate of doing this just randomly goes exponentially down. Whereas if you use an algorithm that's called TRPO, which is a reinforcement learning algorithm that's called trust region policy optimization, you actually see that it performs 80 to 90%. It successfully says, yes, this is an unknot, and here's how you see it. Okay, so in my last 5 minutes or so, I want to talk about the last example of applying RL to such a problem, and this is in the context of the smooth Poincare conjecture. And it's slightly more difficult to explain, but for the purpose of this talk, all we had to do is we had to add one more action. So we had these three actions of relating a node to another. Now we add a fourth action, which essentially takes this and turns it into that. So if I have a node like this, with the first three actions, I cannot unknot this. But if I allow myself to do this band move, so I take essentially these two here and turn them into this at this point. Now I can take, let's say, this band here, pull it through here. Sorry. Take this band here, pull it through there, and then I will be left with two circles. So now I have unknotted this knot by also allowing myself to perform this type of operation. And if you can do it with just the first three moves, the knot is called an unknot. If you can do it with these four moves, the knot is called a ribbon knot. And now Ciprian Manlescu is one of the collaborators together with Lisa Picarillo at MIT. What they did is they constructed thousands of pairs of knots. So you get a tuple of knots, K1 and K2. And they said, okay, so now if you can show that K1 actually is a ribbon knot, meaning with these four actions, I can turn it into something like this, but K2 isn't, then the smooth Poincare conjecture is false. So now this is, again, essentially a binary classification problem. Is or isn't this knot a ribbon knot? If you train a neural network to just give you a yes-no answer, this wouldn't disprove the Poincare conjecture, even if it said, yes, it is, and this one isn't, because you couldn't interpret it, you couldn't sort of turn it into a proof. So we would need a provably correct count example. And the way we do this is we calculate some of these knot invariants. And there are quite a few known, actually, that if they are non-zero, you know that the knot is not a ribbon knot. If they are zero, you don't know anything. They could be ribbon, they could be not ribbon. But if they are non-zero, you're certain the knot is not a ribbon knot. So what we do is we go through all these pairs that Ciprian and Lisa generated, and we find sort of pairs where one of them has one of these invariants not equal to zero. So we know this one is not ribbon, and the other one has it zero, so this one could or could not be ribbon. And then we just let loose our algorithm on this other knot and ask, can you prove that this thing is ribbon? And if it can prove it, we know that this Poincare conjecture is false. And essentially by doing this, we managed to rule out of their thousands count examples, we ruled out all but two. So meaning we have two left over where this knot invariants are all zero, so it could or could not be ribbon, but our algorithm could not find a sequence of moves that would eventually sort of untangle it to this. Moreover, we were able to sort of use a database of knots to prove for 5 previously unknown knots that they in fact do have the ribbon property. And people have sort of tried this before with a more brute force way of finding these combinations, but again, so the search space is combinatorically large. So we did something else. We used this type of RL setup, and for us, we were able to find this. For the first one, actually, we found it within a second, or within a fraction of a second. We found the first of these 5 to be a ribbon knot. Okay, so here are the results. So what we did is we took essentially all knots with up to 14 crossings, and then we sort of, again, we compared something like acts randomly with something that has a trained neural network, or something that's sort of just optimized to draw next actions from a given probability distribution. And we saw that it, again, sort of solves knots. If I allow it to try 500 times, it solves essentially 98% or so of these knots within 500 tries. And for the synthetic data that we generated, it reached similar. So in here, for this type of data set, this seems to be a little bit too simple. It solved it in almost 100% of the cases. This one seems to be a little bit harder than these. So here it solved it in 85% of the cases, but still we see again this 80+% success rate of getting a provably correct result using reinforcement learning. And there's again a GitHub page if you want to try out this algorithm. If you want to find a counterexample to the smooth Poincare conjecture yourself, you can download the code and try to run it. But so let me conclude. I talked about ways of getting provably correct results out of machine learning using mathematical data sets. First thing I covered was something that I call conjecture generation. And I explained how we can use Kolmogorov-Arnold networks in this context. They are a powerful alternative that we propose to neural networks. They have the advantage that they are more easily interpretable, which sort of allows you to do some symbolic regression to come up with a conjecture of how things in your mathematical data set are related. And then you can formulate a conjecture and you can hopefully improve it. The second thing I talked about was using reinforcement learning to get truth certificates. So meaning we set up the reinforcement learning algorithm to find the sequence of actions or manipulations that win the game, whatever this means in your case, and either unknot the knot or turn it so show that it is ribbon. And then by looking at how the neural network did this, which is called an episode rollout, this is your truth certificate for this particular potential counterexample. So you can just sort of ask the neural network, what did you do? What did you do? You just follow its trajectory through the search tree. And by doing this yourself, you can verify that indeed the answer that the neural network gave is correct. And we did this to rule out thousands of potential counterexamples, and we proved for new knots that they are ribbon knots. Okay, that's all I wanted to say. Thank you very much.
Thanks very much. So I think we've got time for a few minutes of questions. So if anybody in the room's got questions first, we'll go to you. If not, we'll see if anybody online's got any questions. You have a question?
I've got like a dozen, but
okay. Do you want to ask one of your just dozen questions?
So I had a question specifically on, let's go with graph neural networks. So you've shown feed-forward neural networks for these CANs. Are there additional topologies which you can use which are more promising, or is it always like a linear progression you use to format?
Yeah, that's a very good question, actually. I had a slide on this, but I deleted it. So let me show you the slide. I took it out for timing reasons. So let's look at how, for example, let's stick with the knot example. So if you look at this, this is the knot as a mathematical object, and now you can ask sort of, how do I even feed this to the computer? And one way you can feed it is you can essentially just turn it into what's called a planar diagram. So give a sequence of 4 tuples of integers, which specify the different crossings and whether the things go over or under here. You can turn it into what's called a grid diagram. You can turn it into what's called a braid. So this turns it into words in a non-abelian group. There are all these different types of representations. And now you could ask, look, which one do I even use? Mathematically, it doesn't make a difference whatsoever. They all uniquely represent this mathematical object of the trefoil knot. And there are algorithms that take you from one expression to another. So from a computer science perspective, the representation matters very much. So if you have this type of grid diagram, you might sort of be tempted to try to solve this with, let's say, a graph neural network, or maybe with something that is taken from a vision task, let's say a ResNet or something. If you have braid words, they contain the word word. So this might actually map onto something that's done in natural language processing. And we follow this route where we represented knots by braid words for the unknotting problem. And then we indeed trained a transformer neural network to answer just the binary classification problem. Is this an unknot or not? So we trained a transformer because we used the braid representation. If you use another representation, let's say this grid representation, you might want to use a different type of neural network. So the mathematical representation of the data set is equivalent, can inform the type of neural network that you use in the end.
Okay, let's go to Andrea online.
Yeah, hi, thank you very much for the talk. It was very interesting. I was just wondering how CANs, if CANs suffer of domain shift as normal neural networks. So if you train your CAN model on a data set to find the relation between an input and an output, and then you apply the model on a new data set, is it supposed to generalize better than a normal neural network?
I'm hesitant to say better. This depends a lot on a case-by-case study, but in general, sort of, let me go back to this. Where is it? Here. So the generalization is essentially a question about this curve in neural networks. So the blue line is the training error, and the green line is the test error. So now in the beginning, both of them are large. If your neural network has one parameter, but you need something more complicated, you cannot reduce the error anymore. And then you make your neural network bigger and bigger, you give it more and more parameters, and as you do so, it can learn more and more complicated functions. And then there's the sweet spot where the train and the test error is very, very small. If you then start to make your neural network bigger, you're giving it more parameters. What is happening is sort of, for this, the sweet spot would be a line. So you fit the line, essentially, as I said, this was sampled from a noisy line. So the sweet spot would be 2 parameters to fit a line with this. If I give it more and more parameters, let's say 10, then it can learn something like this, some very complicated function. And this is what's called a generalization gap. So your test error, so your train error is still going down, because if I give it more parameters, I can fit these points actually completely exactly. But the test error is huge, because, I mean, if I go from the point 0.0 to the point, let's say 0.05, the answer jumps from 0 to 10 to the 5, and that's most likely not the correct answer. So this has huge oscillations in there, and the answers just get very, very big. So this is why you see that the train error is still going down, because I'm fitting the points better, but the test error is going up. Now, if you make them bigger and bigger and bigger, at some point, what is happening is you get a second descent. So at some point, what is happening in the neural network is not doing this anymore, but it's learning something smooth here. And if you are sort of way, way out here, I mean, modern neural networks have billions of parameters, you see that you can't even get below the sweet spot. And finding the sweet spot is very, very difficult. Giving this neural network just a huge number of parameters is in some sense easier. And so to answer where the sweet spot is, you would have to ask, what is the intrinsic dimensionality of the English language if you want to use a transformer, let's say. And that's, of course, a complicated question. Giving it just tons of parameters is easier. However, giving it tons of parameters makes it very, very difficult to interpret. If you use these splines as activation functions, you see that they also fit all of these points exactly here, because we just constructed them to be piecewise polynomials here that go through all of these points exactly, but it also doesn't have this weird oscillatory behavior in between. So it's probably a good assumption to say, sort of, if I'm giving the point 0.001, I'm not going up all the way up to 10 to the 5, but I'm answering also something that's around 0. So in principle, sort of, if I vastly overparameterize my neural network, or I use other methods to prevent overtraining, like dropout, weight regularization, and so on, there are all these techniques and all these tricks. In the end, I think you can get both to not overfit and generalize well. It's just sort of the cost you pay here is you introduce billions of parameters, which means that you cannot interpret it as well as you can and can't work with much, much fewer parameters.
That makes a lot of sense. Thank you. I guess you can also investigate the different relationship between the inputs given by the splines. If you train accounts in different data sets, and that should also give you a measure of the shift. Yeah. Okay. Thank you.
Of course.
Any more questions in the room?
So I was wondering, how do you handle things like image data and volumes? Like, is it possible to add an additional structure into the inputs, or is it still like a singular output variable?
I mean, in principle, of course, you could, if you have an R to the N output, the easiest thing you can do is you just sort of train N-cans. One predicts the first, one predicts the second, one predicts the third, and so on. So what's the question for cans, or what's the question more generally?
It was generally for cans, because it seems like you were able to use the cans to predict an underlying mathematical function. But if you wanted something like a density field for a nucleus,
no, you could have. I mean, you could have cut off. You could have cut off essentially the can here, not do this last summation here or so. and then you would have a map into R2.
Yeah.
But yeah, so for images or yeah, so the disadvantage of cans is because you need to fit these cubic B-splines or these B-splines in general. And this is less efficient than a neural network, even if a neural network has many parameters. So the question is, if you have an image with, I don't know, 100 megapixels or whatever, it will be interesting to see. There are many things that go into cans that could potentially offset the extra cost of generating these splines and so on. So on the face of it, it's much more costly to train a can. On the other hand, they have a property that you don't need as many parameters. So something that you can do with a billion parameter neural network. I mean, if you think about all the weights, and where do I have an image here? So all the weights that go into superpositions of ReLUs here, maybe this is just learning a very simple function in the end. So if I can just fit this function with 4 parameters, rather than having sort of this million things go into here, this might be a huge improvement. And then so if you have few parameters to do gradient descent on, that might accelerate things. Also, there's something that's called the neural scaling laws. So if you want to make your algorithm perform better, typically you can improve along 3 axes. You can give it more data, or you can train it longer, or you can make your neural network larger. These 3 things typically improve the outcome, the quality of the prediction, or reduce the loss. And they have been found to follow some sort of scaling laws that the ratio of these 2 transforms with some e to the alpha. And depending on how big this alpha is, this tells you, if you like on a log plot, this tells you if the slope of this line is very steep, this tells you essentially if you just make the error will go down a lot if I just make the neural network a little bit larger. And for cans, for the experiments we ran in the paper, we saw that these exponents of the slope of the line with which you improve is steeper than what you find for experimentally for other type of neural network architecture. So you could hope that because this sort of they scale better with, let's say, making them bigger, you might hope that this also offsets the extra costs of training a can. But I mean, yeah, as I said, the paper came out, I don't know, like a week ago or so. So there are many things to do with them. We tried to give some initial motivation or some initial experiments in the paper, but there are many things that can be done with them. And we will see then whether they work also well for image problems, for natural language problems, and so on.
Cool, thank you. So I think we'll probably finish up there. So we'll thank the speaker one last time.
Thank you very much.
So next month will be our last seminar of this academic year. That'll be with Verena Kane of the LHC, who's talking about machine learning at the Large Hadron Collider and all the different ways that it's applied. So yeah, we'll finish up there. Thanks very much for joining us today, Fabian.
Thank you very much.
Have a nice day. Bye.
You too. Bye.